We're going to get started with the next session. So our next session is on graphics and animation. My name is Victor Zordin. I'm going to sit down so my head's not cut off. And I'm going to invite you guys to participate, really make my life a lot easier if you would ask some questions. We have 4 talks in the session. 3 of those will be remote, 1 will be in person, and we'll start the first paper talk now. This will be on future frame synthesis for fast Monte Carlo rendering. And the authors are Zhan Li, Carl Marshall, Deepak Zembar, and Feng Lui.
Hi, I'm Zhan Li. Today, I'm going to present our paper, Future Frame Synthesis for Fast Monte Carlo Rendering. Monte Carlo ray tracing algorithms are widely used to generate photorealistic images for many applications, such as computer games, films, and simulations. However, these algorithms are time-consuming, as they need to sample many rays to shade each pixel. A great amount of effort has been devoted to fast Monte Carlo rendering. A popular category of approaches is to only cast a small number of rays for each pixel, and then reconstruct a high-quality rendering from these few samples by denoising. Another category of approaches is to first reproject rays sampled when rendering previous frames to the current frame, and use them to reconstruct the current frame. Our work is built upon deep learning-based frame prediction methods. They employ different neural network algorithms to learn to predict future frames from previous frames. Given 2 frames, I1, I2, our method aims to predict the sequence of future frames I had 3 to 5 frame by frame. For instance, we first predict I had 3 from I1 and I2, and then predict I had 4 from I2 and I had 3. Below, we describe how our method predicts I had 3. Our network takes as input 2 existing frames I1 and I2, the OptiFlow map flow221, and the OptiFlow confidence map M2. The first step is backward flow estimation. The neural network will predict backward flow 322. We then use the predict flow 322 to warp I2 to I3. As the intensity values of corresponding pixels could change over time, we employ an intensity enhancement network that estimates the intensity differences from the previous frames. Specifically, our method first warps I1 to align with I2 and then calculates the intensity difference map between them. We warp the intensity difference B12 with the estimated outflow to get initial B23. Our method then feeds initial B23 together with the initial future frame I-3 into the intensity enhancement network to estimate the intensity difference map B-23. Our method finally adds B-23 to the initial future frame I-3 to generate the enhanced future frame I-3. There are necessary errors in the predict future frame. For example, when the camera angle or camera location changes, content that is invisible in the previous frames will be visible in the future frame. Therefore, we added another neural network that shares the same input as the backward flow estimation network to estimate a confidence map M3. This confidence map provides an optional step to improve the future frame quality by re-rendering those pixels using the rendering engine. In our experience, we re-render those pixels with the confidence values below threshold lambda of the sigmoid rail. We train our frame synthesis network in an end-to-end engine by computing the losses from predicting 3 consecutive frames I had 3 to 5 from 2 input frames I1, I2 as follows, where LT is the loss from predicting I had T. Delta 3 is 1, delta 4 is 0.5, delta 5 is 0.25. LT has 3 components. LT-L1 is a L1 loss for perceptual quality. LTM is a binary cross-entropy loss for the quality of rendering mask. LT-Re is the percentage of re-rendered pixels. Alpha, beta, gamma are all set to 0.3. To train our network, we built large-scale animation datasets. We produced 120 videos for training and validation, 9 videos for testing. Each video has 461 frames. We also created a second testing set. It contains 6 videos for testing. Videos have 33 to 185 frames. We used Blend Cycles to render 6 animation sequences from the Blender Open Movies and the NVIDIA Open Research Content Archive. These are samples of our UE4 dataset. To build our datasets, we bought environmental resources from Unreal Marketplace. To make our scenes complicated, we imported characters animations from Adobe Mixamo. These are samples of Cycles testing dataset. We use PSNR and LP-IPS for image quality. We use pixel re-render rate to evaluate the actual resources for rendering. We first compare our method to a baseline reprojection method that warps the current frame I2 to the future frame I3 using forward warping. Multiple pixels could be forwarded to the same target pixel. We project N will keep the nearest pixel. We project blend will blend pixels based on the depth values. In addition, forward warping leads to holes in the future frame. We will fill these holes using ground truth pixels from the rendering engine. We use a threshold lambda to select a subset of pixels to re-render using the rendering engine. If the value in the predicted confidence map is smaller than lambda, we re-render that pixel. Therefore, as we increase the lambda value, more pixels are re-rendered. As we would expect, the quality of our future frame synthesis method increases as the percentage of re-render pixel rises. With a similar amount of re-render pixels, lambda at 0.2, our method significantly outperforms the baseline reprojection approaches in terms of both PSNR and LP-IPS. This is on Cycles testing set. These are visual examples of comparisons with reprojection methods. Reproject NN tends to generate results with aliasing artifacts, while the results from reproject blend suffer from the ghosting artifacts. In contrast, our methods can predict higher quality future frames. These are another examples of comparisons with reprojection methods. We also compare with other deep learning-based video prediction methods. Here are the numerical results. To ensure a fair comparison, we only train our network to predict one feature frame using the L1 loss and generate the prediction results without re-rendering unreliable pixels in this test. Our method achieves better quantitative results than those video prediction methods with a large margin. These are visual examples of comparisons with video prediction methods. To ensure a fair comparison, we did not re-render pixels in this test when producing our prediction results. These are another examples of comparisons with prediction methods. Compared to those frame prediction methods, our method also generates qualitatively better results. These are another examples. We examine the effect of two components on our future frame synthesis quality. The first is our intensity enhancement network, which compensates for the intensity interference. The second is outflow confidence mask, which is used as the part of the input to the backward flow estimation network. We compare 3 versions of our method: our full method, our method without intensity enhancement, and our method without intensity enhancement and without inputting the confidence map to the backward flow estimation network. As shown in the figure, these two components both help our method predict future frames. This is a ablation study on cycles. We observed that our future frame synthesis method still cannot handle several challenging scenarios. As shown in this figure, our method as well as other methods fail to preserve the fine structure, the silver thread. Our method also cannot deal with significant view-dependent effects. This figure shows such an example where the reflection in the mirror is not predicted accurately in the pointed area indicated by the orange arrow. In the future, we would like to extend our work by utilizing gbuffer data. We hope to overcome existing artifacts by adopting more powerful network architectures. We would also like to speed up our method. It takes about 20 milliseconds to predict 1024 by 1024 frame using one RTX 3090 GPU. The reported duration includes all the stages of our methods, except running the rendering engine to replace the unreliable pixels with rendered pixels. Here we list and acknowledge the digital assets used in this talk. Thank you for your watching. Please feel free to ask questions.
We have questions in the
Hi, I'm
audience?
Zhan Li. Today I'm going.
Hi, John. Any questions
Hi.
from the audience? Yes.
Yeah, thank you for your presentation. I have two questions, like one small question and a bigger one. I'm just going to start with the smaller question. Like when for this network, you use the past optical flow to predict the future optical flow, right? In this paper.
Yeah. For this figure, we use the past generated optical flow to predict the future optical flow.
Yeah, but usually in games or in like in video games, we already have the future flow. So why not use it? Usually, yeah.
That's a good question, because one scenario for our method is that it can run on the cloud server, so that when the network is not stable, our system can run in the client server.
Mm-hmm.
In the client machine. That client machine, they don't have this data.
So it's like, for example, in multiplayer games where you don't have the simulation inside of the computer.
For the multiple player gaming, this is one case. Another case is cloud gaming, that the game is rendering at the cloud server,
okay.
And the client they want to receive that data.
Okay. So
yeah.
That's great. And so for this prediction, are we using when we have I2 and I1 and the past optical flow? Is it using like the previous predictions, or is the good, like, can it handle error accumulation? That's my real question. It's like, if you take the output, you put it back in the input, and you continue doing this, does the network, like, is this method handling that, or
that is a good question. Since this is just a prototype, and in real life, we may restart the render system so that we can have the first two frames if the quality of our prediction is very bad. But for our paper now, we just use the first two frames and then predict the future frame 3, and then we use the past frame 2 and the future frame 3 to predict to generate the future frame 3 to predict frame 4.
Mm-hmm. Okay, so that could be a future. If
you
yeah. Okay, thank you very much.
Yeah. Thank you. Yeah, that's a good question. Yeah.
Thank you for the question. We have a question from the Discord channel. Could you talk a little bit about timing, in particular about the time that's saved by not rendering pixels against the time used to do prediction?
As we reported in paper, the time for our network is just for the prediction step and the prediction step for the outflow, warping, and the mask generation. So we don't report the time for generate the ground truth pixels to replace that pixel that we didn't report. And ideally, it should be proportional to the number of pixels we needed to render.
So give us a ratio of how much time versus the ground truth in some context?
In our, it's like about 8% if we replace our 8% of pixels to replace to replace the bad pixels.
Okay, thank you.
8 to 10%, yeah.
One last question myself. This is compared to two different error metrics. Is there a way to quantify it with respect to human perception in either in the field or in an error metric specifically?
First for the LP IPS, it is already a potential metric for the quality. And I think in the future we may do some user study so that we can tell that the quality of our method is good or not.
Thank you. And thank our speaker one more time.
Thank you.
We're going to move on to our second talk. This is Fast Vortex Particle Method for Fluid Character Interaction. And
hi everyone, and welcome to this presentation on the Fast Vortex Particle Method. So this is a method we developed to improve the way characters interact with the fluids in games. So in particular, like if you have some smoke or mist, or someone is shooting like a fireball at you, this is some sort of gaseous fluid, and you would want that to collide realistically with very complex geometries, like characters in a video game. And so there are sort of two key challenges to this problem. The first one is you need a fluid solver that's efficient enough that you can actually use it in a game. So while you can do that fluid simulation in real time, that's not really good enough for a production game. So typically there's a lot of stuff going on in each frame, so you need a very, very efficient fluid solver that can do a lot better than real time in order for it to be practical. And so the other problem is that you need some representation of your geometry that you can use at runtime, because you're not going to know how your character geometry looks in each frame beforehand. And so you need to have some representation of the geometry that you can use in your fluid solver. And so you don't really have time to like voxelize your character mesh or find the distance to a surface or something like that. That would make it too expensive to be used in a production game. And so our proposed method is based on a vortex representation of fluid state. So this is a bit less common than the more like common velocity pressure based approaches. But in a vorticity based fluid solver, you represent the fluid as the swirling of the fluid basically. So as you can see, the vorticity is defined as the curl of the velocity field. And you can use the Biot-Savart law to then recover the velocity field everywhere in space by taking this integral over the vorticity field and then taking the cross product with the kernel. And so the way you choose to discretize your vorticity field is basically what decides what kind of vortex method is it. So in our case, we choose like the simplest approach, which is to use particles. So each of these particles stores a vortex vector. And so in order to recover the velocity field anywhere in space, you just add up nearby particles. So you actually need to add up all particles, but we use this approximation, which seems to be good enough for games. So you add up like nearby particles in order to get the velocity field in a point. So the first thing we do basically is we evolve this vorticity field in accordance with the vorticity version of the Navier-Stokes equations. So this is sort of like a free space solution to the Navier-Stokes equations, and then after that we do the collisions with the character geometry. And so as you can see here on the right, there's sort of these vortex particles that are scattered across the geometry, and they sort of take care of the collisions. And then you have these free-flowing vortex particles, and they sort of take care of the swirl in the fluids around the character. So in order to just explain a bit more about how the momentum equations work, there are sort of three things you need to simulate. There is the advection of vorticity, and that's easy because you just store a vorticity vector on each particle. Then you need to simulate the vortex stretch, which is the vorticity field is, well, it's stretched in the velocity fields. And finally, you need to take care of vorticity diffusion. And so I'll refer to the paper for a more detailed derivation of how we do this. But these are sort of the components you need for the free space solution. And once you have a free space solution, we evaluate the velocity field at the surface of a character. And we do that at these discrete points that are scattered across the character and are actually not dependent on the underlying high resolution mesh. So these can be scattered in any way that is sort of efficient. We use 256 particles, and so that's not a lot, but it still gives some very detailed collision. And so what we do at all these 256 points is we evaluate the velocity field from the free-flowing vortex particles, and then we initialize a divergence-free collision field. And so we use the relative velocity between the surface might be moving as well, and the surrounding fluids, and we can then set up this collision field by using, basically, first we use Rankine sources, which are like monopoles. We then measure the tangential velocity at the surface, and we use that to instigate vorticity around the character surface. So here on the right, you can kind of see the effect of tuning this vorticity generation at the surface of the character. So in the first slide to the left, there's no vorticity generation at the surface, and you just get this sort of laminar beam field, and you can then tune up the vorticity generation in order to get more and more swirliness around the character. So this is connected to the friction between the fluid and the surface. And so for rendering, we actually just use a lot of passive advecting particles. So if we have these very few vortex particles, we update those according to the Navier-Stokes equations and the kinematic boundary conditions on characters, on the character geometry. And then we evaluate the vorticity field, the velocity field in a grid around these vortex particles. And we then use, well, it can be actually millions of passive tracker particles to actually visualize the effects that we're trying to draw at runtime. And so this gives a very, very sort of detailed swirling motion, but our method can also be used with volume velocities, volume fog volumes and stuff like that. So you could store like a density on a grid and then advect that, and you would have volume smoke, for instance. But this representation gives a very sort of good idea of how detailed you can get the turbulence around these characters. And so to actually show some simulations, here's sort of like the first one where you got this character moving about in what is initially a laminar beam of particles, and as they sort of hit the character, you got this turbulence generation at the surface. So this is where you can sort of have vortex particles being generated and initialized at the surface, and then they are advected in the surrounding fields. And so you get this sort of very, very detailed swirly motion. And so another thing, well, this is a more challenging example where you have got this sort of buoyant plume, and so the velocity field on the character surface is more complicated, and so at each time frame you map the velocity field down on the surface in order to generate this divergence-free collision field. But as you can see, even with 256 particles on the surface, it still works fairly well. And so this other example is sort of like some blue smoke coming out of some other character. And this is a bit more challenging, but you can still see when he's sort of waving his arms, he sort of moves the smoke around him. And so in terms of performance, this method is really, really quick because it doesn't actually require a pressure projection step or anything like that. And so we made these sort of benchmark examples where you can sort of see how quickly it runs. So there is the time it takes to actually update the physics, and that's below 0.3 milliseconds in this case. Then it takes some time to actually move all these particles. It might be millions of these tracer particles in that velocity field. And that's actually the bottleneck of our method. So as you can see here, we increase the number of tracer particles, and you can see how that affects the runtime. Although, as you can also see, the dynamics are actually the same. So these detailed dynamics take no time to actually simulate almost. And the bulk of the simulation time is actually just moving particles in the field you get from the vortex particles. And so you also see some frame rates here. So this is for the entire simulation. These are simulated in Unity. So for the entire simulation and rendering, you can see you get the frame rates listed here. So these are quite quick. So the middle one might be feasible in a production game. The last one is probably a bit too heavy for a production game. But again, it really depends on how you represent the fluids, and you could use other representations, or these tracer particles could be bigger and maybe be animated in order to sort of represent a bigger chunk of the fluids. But here they're just points, and then you need a really, really large amount of particles to actually make it appear as if it's a continuous fluid. And so with that, let's see if there are any questions.
Thank you for the presentation. Do we have questions in the audience? I'll start with one. I, of course, have to ask this question about character animation too. So is there a way to get the feedback from the fluid to change the character's motion? How would you do that?
Yeah, I mean, we didn't investigate that actually. But I mean, it is possible to, of course, get the velocity field at the surface. So this is a good feature of vortex particles because they actually create continuous fields. So you decide where you get the field. So in this case, we use the grid because that makes it very easy to interpolate to a lot of these tracer particles. But one of the cool features is that you can get the field anywhere on this high detail surface. And so, well, the more particles you use, the better the collisions will be. And you could use it for, I mean, a collision as well to move the character.
Seems like there's an opportunity there. We have a question on the Discord server. Any thoughts about how one might couple fluids simulated this way to the secondary characters, effects like cloth or hair or fur on the character?
Well, I guess it's a bit the same the same thing. You can do anything with this method you would do with any other fluid solver, basically. So I can't see it wouldn't be possible to do it with the cape as well, or anything like that. But of course, what you'll need then is you'll need to have these collision particles on your hair or fur, and then as you move that, you'll have to measure the relative velocity field between your cloth and your fluids.
Okay, thank you. Questions from the audience? I have one. Go ahead.
Hi, it was a wonderful presentation. I really enjoyed it. So before I ask my question, I just want to confirm that I understand the concept first. You're using a set of vortex particles to determine, or rather create a velocity field, and then using that field to further advect your actual render particles, right?
Yeah, that's right. So I mean, there is a intermediate stage, and that is if you try to just get the velocity field at all these tracer particles, like right from the vortex particles, you're not going to have something that's very fast, and so you use this grid as an intermediate buffer. Then you can trilinear interpolate to the tracer particles. But you could also use like a combination. So it's just because it's convenient to actually map the velocity field from a grid to a lot of particles instead of directly between vortex particles and tracer particles.
That's awesome. And the other question I had was, did you ever try experimenting with multiple different fields, advecting particles through, say, two different velocity fields to represent different types of flows?
No, we didn't do that. It should work. I mean, I don't. When you say maybe you mean like you have two flows from different directions or something like that. So you would want like the fluids to collide. You could do that. We didn't experiment with that in this case. So we tried these beams where it seems to work fairly well, but it's also because the character is sort of a small compact geometry. So these methods are you might need something else if you collide with like a big surface or something like that.
Okay, I was just curious because if you're imagining, for example, a character where you have two different fluids of difference with different viscosities colliding with the same character, I was curious to see how the method would hold up in terms of when the two different fluids collide.
Yeah, well, we didn't try that. We haven't tried that, but it would be cool to try it out.
Yeah. Awesome. Thank you so much.
The question, thank the speaker. We're going to move on to the third paper, Active Learning Neural C-Space Signed Distance Functions.
My name is Xinghao.
For reduced deformable self-collision, and we're really right along.
Hi, and I'm going to present Active Learning Neural C-Space Signed Distance Fields for reduced deformable self-collision. This work is also done with Ulrich Kovold, Alec Jacobson, and Paul Cry. In real-time simulation, fast self-collision detection has been studied a lot since the time cost for SCD can be a bottleneck if not handled properly. On the other hand, reduced deformation is also an important technique since it can largely reduce variable numbers in equations of motion. Babik and James proposed an inspiring work on reduced model self-collision, where they pre-compute conservative certificates which can be considered as ellipsoid bounds in configuration space. When the configuration is within this boundary, then there is a guarantee that the corresponding part of the model has no self-collision. The idea of our work is to learn a more exact boundary, such as the red line with neural networks, and what's more, assign distance field which can be used for self-collision detection and self-collision handling in real time. In reduced models, the deformations are reconstructed by weighted sum of deformation modes. The video here shows 3 modes of a bracelet model. During simulation, the modes are arranged in a matrix U, and we can use a configuration vector Q to represent deformation. We define the C-space boundary as a set of configurations that make the reduced model just have self-contact. For the bracelet model with the first 2 modes, its C-space boundary is shown in this red line. This configuration is on the boundary, and the bracelet is just having self-contact at its ends. When the configuration is on the positive side, the bracelet has no self-collision. If on the negative side, the bracelet does have self-intersections. If we define the distance of a configuration as its Euclidean distance to its closest point on the boundary, we can visualize this 2D SDF. We can consider the C-space sign distance field, or SDF, as a mapping from the configuration to self-intersection state. The sign distance not only shows whether a reduced model is in self-collision or not, but also stands for how far is the model from the closest self-collision, or how deep is the model trapped in self-intersection. Our goal is to use a neural network to learn this C-space SDF. However, learning such SDF has 2 difficulties. First of all, when the reduced model has multiple modes, learning the SDF in a high-dimensional space requires a lot of samples. Second, for each configuration, we only know its sign by performing self-collision detection, but not its distance. To address the first difficulty, we make use of active learning, which automatically chooses informative samples for labeling. For the second issue, we use iconoloss and introduce a 2-pass learning method to inject approximated sign distances. To sum these up, we use active learning in both passes. In the first pass, we first generate exploration samples and exploitation samples, which are then queried for their signs by performing self-collision detection. These signs are compared with the network predicted signs for the sign loss in the loss function. In addition, iconosamples are independently generated, and their gradients contribute to the iconoloss term. At the end of the first pass, the accumulated samples are exported as a point cloud. The second pass is similar to the first pass, except that we use the point cloud to provide approximated sign distances, which contribute to the sign distance loss. For exploitation, it finds samples that cause most uncertainty for the predictor. In our case, we use this equation to find the samples closest to the current prediction boundary from the random data pool. This video visualizes the exploitation samples in violet dots. We can see as the predictor boundary approaches the ground truth, the exploitation samples also become more valuable since they also drop on the ground truth boundary. However, learning with only exploitation samples can cause the neural network to miss disconnected regions. Also, the network is slow in learning the sharp features. In this example, the exploitation samples completely miss the bubble because the whole bubble is misclassified as red dots. And since only a short part of the orange line is within the spike, only a few samples will be picked here. In this example, when the prediction converges to the apple body, the learner can no longer learn the leaf with only exploitation samples. That's why we include exploration samples, which are used to find disconnected regions and sharp features. In our approach, we first uniformly generate a few samples within the domain. Then we select those samples with wrong sign predictions. In this example, the predictor converges to the apple body at first, but we constantly have samples within the leaf area, and the learner finally starts learning the leaf. We also have an icono-loss term in our loss function. Since the C-space SDF represents the Euclidean distance to the boundary, the gradient size should be 1. The icono-loss helps stabilize the gradients over the sampling domain. This is a function measuring the difference between the gradient magnitude and the desired value. We use a piecewise Nike function to restrain the gradient size in a bias region close to 1. To learn the SDF better, we also inject approximated sign distances in the second pass. We have observed that in the later stage of active learning, the selected samples are likely to be close to the boundary. Therefore, the accumulated samples from the first pass can be a natural point cloud that covers the ground truth boundary. In our method, the approximated sign distances are computed by finding the closest points with the opposite signs. This video shows the final result of learning the SDF of the apple. The network not only learned the boundary very well, but also the SDF. This Twitter example is also interesting because it has a lot of spikes which are hard to learn, but the result is also nice in both terms of the boundary and the SDF. In real-time simulation, performing SCD is simple. We just test whether the network output is less than 0. For self-collision handling, the gradient of the SDF provides a direction to the closest boundary point. In order to prevent a model going deeper into self-intersection, the network evaluation in the next time step should be greater or equal to the current one. Therefore, we can derive the constraint equation as below. Here, the JK is what needs to be fit into the constraint Jacobian matrix, and the column vector here is the time derivative of the generalized coordinates. This video shows the bracelet model with 3 modes. The network detects self-collision as soon as the bracelet has contact between its ends, and the collision response prevents the upper part of the bracelet from sliding into the lower part. This is a spring model with 3 modes. The network detects self-collision as soon as the spring is compressed to have self-contact. However, the learned boundary has to be very precise for good visual appearance, and learning such high-quality SDF for the high-dimensional space is still a hard task for our method. The examples here show a snake model with 7 modes and the bunny model with 10 modes. The self-collision detection and handling is not working well because the learning results are not good enough. In conclusion, we propose a learning method to learn the C-space SDF. We use active learning to improve sampling efficiency, use icono-loss and approximated distances to learn SDF from signs, and also use the network gradient for self-collision handling. We still have a lot of things to improve. We need to improve the learning result for high-dimensional space, either by finding new sampling method or new network structure. In addition, since the SDF gradient does not correspond to the geometry normal, the proposed self-collision handling does not include friction. Thank you for your listening.
So our speaker is here and
Oh.
ready to answer questions. I'll get us started. I know in the paper you mentioned something about friction, that there was no way to do friction modeling. Could you mention that for the audience?
No, I think that's just a deficit of our paper. Is that we couldn't use the we couldn't use the learned SDF for identifying the normal direction. So as a result, we cannot like provide a good friction that is pretty much related to the normal direction.
Yeah, so that was related to my question. I wanted to understand if you could, at that point, take the contact point and assess the surface, or if that would just be too expensive and defeats the point.
Sorry, what's the question again?
Now you have a collision, you know that there's a collision. Can you assess the surface at that time and determine the surface normal because you know there's a collision? That was my question.
So let me repeat your question. So basically, when you have a self-contact, you are asking like how to like identify the normal direction.
Kind of. I'm trying to say that if the collision is detected, your system tells you there's a collision. Is that helpful in now determining the normal by looking back at the geometry? And does that, or that defeats the savings of the system?
I think you really have to like really consult the real geometry to identify the normal, because the normal in the SDF doesn't really like give you a real normal in the geometry side.
Okay, we have a question in the audience.
Hi, Jinhao. Thanks. Nice work. I had a question about I think it was the exploration samples that you're generating. So you generate these additional exploration samples to find out where you've missed maybe some holes or sliver geometries like in the field. And so I was wondering, is it possible that you could still miss some of these sliver geometries depending on the density of that sampling? Like, do you have to tune this? Like, how do you go about tuning this density of?
Yes, this can really happen because, like, for example, if you have a model that have like multiple modes, then the C space is going to be like in a very high dimensional space, and it is very likely that you have some little tunnels like in some high dimensional space that you cannot really. I mean, the exploration samples is sort of like a relief to just the exploitation samples, because without that you can like you are very likely to miss some of the regions, because if you are going to identify those bubbles, it's pretty much like totally relying on the initialization of your network. However, if you have some like exploration samples, you can add exploration samples a little bit like at each step, and in the hope that the accumulated exploration samples, with that you can identify those like previously unidentified regions. But this is also very likely that your exploration sample is still not enough, that you miss some of the tunnels or the spikes or some bubbles like in some high dimensional space that you don't really find.
Great, and our speaker's here, so we'll ask some questions in person this time, and I'm going to move us along because we're running just a little bit behind, and go on to the fourth speaker. So the fourth presentation, thank you so much. The fourth paper is called Meta SVG, a portable exchange format for adaptable laser cut plans, and the presentation will be online.
Hello, everyone. I am Jim McCann. Hello, everyone. I am Jim McCann. I'm a professor at Carnegie Mellon University, and I'm going to be presenting the work MetaSVG, a portable exchange format for adaptable laser cutting plans. This is work with PhD student Nuri Yildirim, who is co-advised by John Zimmerman and myself, along with students Matthew Franklin and Daniel Zhang. Let's talk about the state of the world. Right now, many laser cutting plans are authored as parametric 3D CAD models, which can automatically adapt to different cut widths, scales, material thicknesses, and material types. However, laser cutting plans are shared as static 2D vector graphics files and require hand editing to adapt. So in this instance, there's a laser cut dice plan, and you can see it's downloadable as CorelDRAW or SVG files, both of which are 2D vector graphics files. If I want to adapt that for a thicker material, I have to edit the file by hand in, say, Inkscape. So in summary, exported laser cutting plans lack parametricity. Past attempts have tried to remedy this lack of parametricity by making joints that work over a wider range of materials and cut widths, or can self-correct for, say, cut widths, or by trying to recover three-dimensional information from 2D paths, so basically trying to hallucinate the CAD. And if these approaches don't work, there are also dozens of custom editors, so you may not be able to use the laser cut plan that you downloaded, but hey, at least you're going to be able to make a new one. What we decided to do was to see if we could export just enough parametricity to allow plans to be adapted to new materials, etc. And we did that by using a new format we call MetaSVG. MetaSVG is a standard SVG file, but it has extra information embedded in a metadata tag. Particularly, it has blank part shapes, that's part shapes without the joints, and joint parameters. And this extra information allows one to adapt the pattern to all sorts of different materials, scales, and thicknesses. So let's talk about the CAD system we use in this project. As input, our system takes Onshape files. Onshape is a cloud-based CAD system that allows easy sharing of feature scripts. That's custom code that generates parts of shapes. And particularly, we wanted to use Onshape because it already had some good feature scripts for dealing with laser cut features, particularly the laser joint and T-slot joint features developed by Arul Suresh. We used these features in our project, although we modified them just a little bit to add a little bit more metadata for export and a joint fit parameter, which is super useful. In the end, we built a system that supported 4 joint types. Box joint and T-slot were the joints I talked about before. Tab and slot is a modification of box joint, and slotted is a joint that we cooked up on our own. So we get the data about these joints out of Onshape with an exporting script. The exporting script is written against the Onshape API, which is a HTTP REST style API that allows you to get and manipulate CAD documents in the Onshape cloud. What our exporter actually outputs is the part shapes. It just reads those out of the file, and then it disables all of the features, effectively removing the joints so that it can get clean part shapes, and finally it extracts the parameters for each joint. All this data is stored in a MetaSVG file. And a MetaSVG file is just a regular SVG file that has some extra metadata in it, particularly the blank part shapes and the joint parameters. The joint parameters that are stored are the joint type, alignment, fit, angle between incident faces, and per joint type parameters. All this data gets used to adapt the file for cutting. That's done by a little utility we call MetaSVG print. You input a scale factor and then information about your material, like its thickness. You can annotate what your cut settings will be, since some of these values actually change based on cut setting. The kerf, that is the cut width, and some compensation factors for the various joint types and the various joint fits. And now all of this stuff can also be saved as presets, which is pretty useful since you generally get your materials dialed in once and you can just flip to them and print. Now what actually goes on when you press export cut plan is the blank paths are loaded, edges corresponding to each joint are found by the code, and geometry is generated for regions that should be added or subtracted for each joint. Then that geometry is modified based on the desired fit values and, of course, the kerf, that is the cut width. And finally, Boolean operations are used to compute the final cut paths. And that brings us to some results. So here are results on scale change. Of course, changing the scale of a pattern is very annoying by hand because you have to redraw all these tabs. With MetaSVG, all the tabs get rescaled to be appropriate for the material thickness. Here's a result of material change. When changing materials, you have to be particularly cautious about fit. MetaSVG's fit tables really help here. So what you would use as a friction fit on wood would tend to shatter acrylic, for instance. And finally, here's a thickness change result. You could see going from a thinner to a thicker plywood, the overall pattern shape is preserved. All right, let's wrap up with some discussion. So we wanted to know how applicable this MetaSVG system actually is to cut plans in the wild. So we did a survey of cut plans on Thingiverse. We looked at about 1,500 laser cut objects on Thingiverse. We categorized them based on whether in dark blue the current system supports them. In lighter blue, the system would support them if we added a few more joint types. So you can see down at the bottom the kind of joints that we're talking about that would need to be added. These tabs in the middle of faces. And in very light blue, we have trinkets. These are things that don't actually have multiple parts slotted together, so are trivial to adapt. MetaSVG supports them, but you don't get any benefit. And finally, there are a few things that are not supported, about 7% of all the models we looked at, and those are models that do things that violate the basic assumptions of MetaSVG. For instance, they do kerf bending. So taken together, you can see that the MetaSVG idea would work pretty well for a majority of existing cut plans, and so it does seem viable in that sense. Okay, and just a few concluding thoughts to wrap up. First, MetaSVG is about lightweight parametricity. That is, it's less expensive to evaluate than a full CAD document, but more useful than a static document. And I wonder, what's the right way to do this in general? Not just for laser cut features, but for all features. See, for instance, the idea of CAD configurations that many CAD tools already support. Maybe there's a way to build on that. And secondly, I think this fit parameter is really interesting because this is a qualitative parameter. And qualitative parameters generally require different CAD approaches than quantitative ones. And so I think it's interesting to consider how one might go about building general qualitative CAD tools. Okay, so that was MetaSVG, our lightweight parametric approach to distributing laser cutting plans. If you want to ask questions, you could of course do so now. Also, all of the author contact information is available along with code and the paper itself at the website. You can see the URL right there on your screen. So I hope to hear from you, if not right now, then soon.
Thank you for that presentation, Jim. Do we have questions from the audience? I'd like to start with one. On the joint that's like a box joint, your models, as you scale up and down, keep the same number of tabs. I don't know if that's the technical word for it. Is there a benefit for changing the number of tabs and maybe making that part of the parametric model?
Yeah, it is part of the parameters that are actually used to recompute the joint, but it's not adapted. I think there could well be an argument for including it, particularly for things like a friction fit, where you might want to adapt the total amount of contact area in order to increase or decrease the friction of a friction fit.
Right, yeah. Questions in the audience or Discord? While they're thinking them up, I have one more for you. I know this is about SVG, but do you think this would fit in a 3D printing setting where you're thinking about slices of a 3D printed print?
Yeah, so this project really came out of thinking about why is it that we see so much more sharing of 3D printed models than we do of laser cut models. And I think that it really does come down to file format. What people share when they share 3D prints are 3D shapes, and then they run them through a slicer on their own to come up with a series of actions that produces that shape. But when people are sharing cut plans, they're often sharing an actual cutting path, not the thing they want to get out. So there's this sort of philosophical disconnect between sharing the target and sharing the actions. And sharing the actions seems to be the worst strategy. So I think that maybe in 3D printing, people are already doing it right.
Okay, we have a question from the Discord. I'm not sure I understand the question, so maybe I can read it directly and you can interpret it for us. How do you handle joints to pattern overlapping? Joints to pattern overlapping?
So there are a couple of kinds of overlap that could occur when you're doing pattern adaptation, and I'll talk about how the system handles both of them. The first is you could be making tabs longer and they can run into each other between pieces. What our system actually does is it adapts each piece and then it lays the pieces out after adaptation. So that kind of overlapping, not a problem, but that's the easier kind. The harder kind is if you're making tabs deeper and they run into each other within a piece. And in that case, our system is pretty inelegant. The way that it synthesizes joints is it computes a mask of all the material that should be removed from a given part based on all the joints and all the material that should be added. And then it, I think, adds all the material that should be added and then subtracts all the material that should be removed. So if you have things that run into each other in the removal mask, then what will happen is that you might disconnect your pieces. But of course, there was no right answer in that case anyway. So doing an expected thing seems okay to me.
Right, thank you. Let's thank our author and our other speakers as well, and we'll finish the session.
Okay, just need a minute here while we switch gears. I'm supposed to go over there, is that right? Can we just, thank you. And, no, okay, go. Adrian is tech support, camera guy, mic guy. Could I project my slides? Please? Sorry, sir. We'll just be a minute. There we go. Okay, so I have the honor and privilege of presenting our first Canadian Human-Computer Communication Society awardee, and that is an Early Career Research Award. And this award is for outstanding work in graphics or HCI, there's 2 awards, or another related field, and for somebody who's been an academic for less than 5 years, so tenure-track person. And the winner of this year's award is Sarah Nabil, and she is an assistant professor at Queen's in the School of Computing. She's also the director of the iStudio Lab at Queen's, and there's her office number in case you want to go visit. So you can go visit. And she's also a new mom, and very proud of that. Her research focus is in software design with interior clothing and or on-person design. So Jim, I know you're not here, but you were here. You probably want to talk to her about buildings and things. She does a lot of work with soft sensors and smart sensors, wearables, and you can see she sews. So she uses a sewing machine. That's pretty cool. And of course, she's extensively published in our venues. You know, GI, of course, is the most premier one, but UBComp and Chi as well. So her publication list is quite extensive, and she's going to be a force to be reckoned with in the future, for sure. So Sarah, please come up. You're going to give us a talk for 20 minutes. Thank you. Am I right? Yeah. She's got great reflexes. Well done. We'll just take it. So, Sarah, come over here with your microphone, so you don't drop it. This is her little award, which is hard to see in the plastic, but I'm going to keep it in the plastic. But it's a nice little award.
Thank you so much.
Congratulations.
Thank you.
I'm going to bow because we're worried about COVID. All right, thanks.
Thank you so much, Deb. I'm really honored, and I can't believe I got this, but thank you. Thank you so much.
Oh, it's most deserved. I'll do your computer.
Okay.
Again. My rightful place in the chair.
Okay, thank you so much. This was a really great intro. Let's see if this thing works. Yay! Okay, so I'm Sarah. Hi, everybody. And yeah, I'm so honored to be here today taking this award. It really came as a surprise to me. So it means that the community, I guess, appreciates whatever I do. So yeah, I'm an assistant professor now at Queen's and heading the new iStudio lab at the School of Computing. Before that, I did my postdoc at Carleton and my PhD at Newcastle University. Open Lab, and therefore I want to thank the people who I believe made who I am, my PhD supervisors, Dave and Thomas, Professor of Digital Living at Newcastle Open Lab, and Professor of Ubiquitous Computing at JTech. And of course, last but not least, Audrey, my postdoc supervisor. I can't thank her enough for all her mentorship and inspiring work. So, my family, above all, who I guess also contributed so much to what I've been able to achieve. My great husband and my lovely daughters who insisted on coming all the way here. That's a better photo. And thank you so much, girls. You've been through a lot with me. Thank you for bearing with me. Okay, so last but not least, let's go into this. So what I do is basically interior action design. I kind of needed to invent this word to blend both worlds together, interior design with interaction design. So what is interior action? I guess it's interactive architecture, interactive interior spaces, interactive artwork. And in order to be able to do that, we sometimes need to work with novel materials and invent novel fabrication methods. And we do those two things at the top to be able to support the one at the bottom. People who are underrepresented, generally from mainstream and commercialized technology, and marginalized groups. So let's start by seeing how we do these three things. But before we start, let's look at what kind of materials we use at the lab to be able to do these things. So instead of using electronics and off-the-shelf electric components, we kind of sometimes need to use smart materials and things that materials science has given us to be able to embed physical interactivity within the physical world. So conductive materials, smart fabrics. Imagine everything's around you being able to be interactive, but not having visible electric ports. Like, for example, these conductive fabrics that look as normal as you would see, but it acts as a double Fresnel sensor. Or maybe resistors that are basically just stitches out of a sewing machine. And of course, while sewing, you need to do a lot of multimeter measurement, right? And then think of even audio speakers that are made out of digitally embroidered spiral patterns with silver-plated or conductive threads. So basically, the fabric itself acts as the actuator. Okay, there are also color-changing pigments that you can use to dye everyday things like yarns and fabrics with color-changing capabilities that respond to heat, light, or hydrochromics that respond to water and humidity. My favorites are shape memory alloys, or basically threads that can be physically programmed to change their shape. And therefore, if you embed them within the material you're working with itself, you're able to make that material shape-changing and electronically controllable. So with those kinds of smart materials, we're able to innovate new fabrication methods that would enable us to make everyday things around us, whether it's wearables or interactive things in the space, have sensing or actuating capabilities. So here is a video that shows some of this and how we do it. I hope it works. Right, so these are the kinds of materials that we use, and these are some of the fabrication methods that we develop at the iStudio. And what we do is basically, like I said, those three main pillars of enriching people's experiences, embellishing everyday things with interactivity, and empowering people who are mostly marginalized groups. So let's start with the first one and see what kind of things can we enrich. So experiences, think of your everyday life. You're just going out and about in the cold Canadian winter, and then you're having your winter hat on, but you also want to have your speaker, your headphones, or your earplugs. And basically, it's either put those on top or inside, and some people really find them annoying. And what we did with the digital embroidery method that we talked about earlier is that we were able to embed the speakers in the fabric itself. And the nice thing about this project is that it was inspired by what people wanted. So we actually talked to users about what they want to design, and they came up with what they needed. And they sketched what they needed. We brought a domestic embroidery machine in that is accessible. It was more like a DIY method where they played with it, and they embroidered the conductive thread on the hat's fabric itself to make what they wanted. Another piece here, like what you've seen in the video, this one was for the Living with Adaptive Architecture exhibition, and it was to experience the interactivity with the invisible members of our ecology. So bacteria and viruses that we already interact with, but it's invisible, it's unseen, right? But imagine having an interactive piece of wall art where it's designed through a bacteria-inspired pattern, and then it has color-changing and shape-changing elements in it when people touch it or come close to it. And then we study how people interact with it in the exhibition setting. Here's another piece that was fun to make because we collaborated with a pharmacy chain in the UK, and we ended up making for this interactive pharmacy space a lot of squishy toys that you can play with, but those are embedded with seamless color-changing threads dyed with thermochromic pigments and conductive yarns, and so people were able to play with them to see the difference between sort of like the good bacteria and the bad bacteria that you can interact with them on your daily life. And then it was displayed at the London Design Festival in the UK. So yeah, let me skip that. Okay, here's another piece that also contributes to a social experience, but within maybe family members or a group of friends having dinner together. This interactive table runner actually changes its shape on a dining table while people are having a dinner set around it. Let me show you how it actuates. Here's another version of it. Okay, so enriching experiences in our real life, in our physical world, right? But then there is also in our physical world, in our homes, in our workplaces, all the kind of decorative things that we buy, we create to embellish our spaces, right? How about would we think of these things if they have interactive capabilities, if they can do more? If they're not just there for aesthetics, if they have sensing abilities or actuating power embedded seamlessly within them, without looking like devices, without being gadgety or anything. Let's look at some examples, like, again, the Soft Speakers project, which yielded a lot of interactive furniture with speaking capabilities. I think I did that one during the pandemic when I was locked down with my husband at home. We're both doing remote meetings all the time, and I sort of wanted my space. Obviously, at the beginning, none of us had home offices, and I was like, what if I can buy an IKEA chair and hack it and have speakers embedded within it so that only the person sitting on the chair can hear the meeting without having to wear headphones all day long, right? And so let me show you a video of how this project went, including the talking toque. So that was a pretty cool project, but think of all the other things that we get in our homes, in our spaces to kind of add identity, add personality, add decor to it, add our personal touch. What if these things can have interactive sensing or actuating capabilities to it? So like your vase, what if it can interact to your placing of flowers or watering the plants, and then it can deform its shape and squeak, or your backsplash in the kitchen, if it is made with thermochromic pigments that can reveal a kind of intricate Ottoman pattern instead of just a gloomy monochrome. Or we did that with nichrome wires embedded inside, so it's also electronically controllable. Or this furry throw, I really love this one, comes in pairs, and we made every pair connecting to each other through Wi-Fi. So you have one at your home and then one at your loved one's distant home, maybe in another country or continent, and you stroke one of them with conductive threads inside, it detects your tactile poke and it sends it all the way to the other one in a form of shape-changing, shivering actuation instead of just a digital notification that comes to their phone. So we did that using shape-changing threads sewn inside. And so you wouldn't interact with this as a device. Some people actually, in our study, described it as cute, and some people said it was creepy. But at the end, they sort of dealt with it as a normal blanket, as a furry throw. And it was quite shaggy in its texture as well. So when it swayed around, it was weird. But yeah, think of all the things that we can embellish, not just with decorative elements, but also with interactive elements. And then finally, think of how these things can be used to empower people and not the mainstream kind of like white male design technology, if you want. So here is an example of a project we worked on with refugees in a refugee camp, and the amount of data collected about how they were decorating their spaces is enormous, and it's striking. They were more decorating their spaces in a refugee camp for escapism, for identity, for expression, and they said to get out of the camp, to feel home. And then this other project was really cool because we did e-textile prototyping, and we almost invented this new method of using punch needling to do e-textile circuits. But then when we talked to our occupational therapists about how to make this method accessible, it was really great study because, well, not great, but I mean interesting, because they said, oh, if you use these accessible and adaptable means, you can make this cuff work with people who might not have hand dexterity as other people. And then you can also turn bilateral tasks that need fine motor skills like needlework into a much more accessible opportunity for people to design their own things. And then, yeah, the nice thing about this as well is that you can always pull it apart and reuse the materials again, unlike other prototyping methods that just destroy the material altogether. This project also, we were working with people with repetitive strain injury, but we were looking more on what current solutions they have. So basically, they need to take micro breaks every 30 to 50 minutes during their work time, and current solutions depend on mobile applications and desktop apps that just hinder their productivity and stop them from work, and like, you have to take your micro break now. And what we thought of that with this kind of technology, sorry, we can actually design things that are already in their workplace and make them interactive to trigger their micro breaks. And so in a co-designing workshop with them, they came up with their own designs. They said, I want my desk toy to give me the nudge, to remind me of my micro break. I want my Snoopy to come down and be like dangling like that and remind me that I need to fix my posture or remind me of my micro break. And we designed a lot of things with them depending on their own needs. In this other example, we worked with people with visual impairment on how to utilize deformation and bend gesture in order to enter their passwords instead of pins. And it was really interesting because they said, oh, I can remember how to do bend gestures much more than I can remember a numeric pin. And it also helps a lot with shoulder attacks. This other project, we were working with people with mobility impairment who have problems donning and doffing. And in the user study, they talked a lot about how they need to wear bigger fit clothes than what they would normally like to wear. And what we said to them, okay, we have shape-changing threads. How can we sew them into your top garments to make it much more a better experience, right? To make it much more better fit to you. And they were like, yeah, we want them here and there. And it was actually way different than what we thought. When we started this project with them, we thought certain other points would be where they want the fit to be to their sizes. But again and again, like you would see with the pattern here in all of these projects, talking with people and including them in the design process from the very beginning, and not just as means for evaluation at the end, really always brings better and different results than what we would have done on our own. And yeah, we would be sewing, shape-changing patterns in their tops, and talking with personal support workers as well about how to make these things. Oh, this is another project that we worked with people with dual identities who are both Western and Muslim, and we thought to make interactive furniture that would project their dual identities. And I think there's a video here. Into the furniture itself. So yeah, bringing some sort of animation or some sort of dynamics to the static decorative things in our everyday physical world. So basically, that's it, I think, for what we do, enriching people's experience with sensing and actuating elements into their interior space and decorative objects, with the aim to empower people who might not otherwise be considered when we think of tech. Thank you so much. Thank you. Any questions? Thank you. Thank you so much.
Wait a minute. Hang on, Sarah. Do we have a question? Are you ready to get one of these things and start to put it in your house? I just have a little question about, are each of these custom made, or, can there be some sort of mass production idea where you can put together pieces, perhaps, and
I never give a talk without getting a question about when I'm going to commercialize this. But I think today's keynote really inspired a lot of what can be done. So far, it's just research, but I'm always getting encouraged to kind of open this for commercialization. Would I find customers, you think?
I love the chair.
Oh, thank you.
There's a question from our virtual audience. Are there concerns arising from the e-materials for safety, like electric shock, or privacy, similar to RFID tags? Can your conductive fabrics be exploited to track and identify individuals in public spaces, or your thermal active threads used for this purpose by manipulating ambient temperature to trigger color changes known to be unique to an individual?
Okay,
we'll go with that one first.
Quite a packed question. Let's break it down. Okay, so are there concerns for safety? As any electronic device in the world, at the end, that's the essence of it. Yes, there would be. It's more like using really any electric device in your home, right?
Don't put it in the washing machine.
Yeah. I also get that too, like launderability of these items, but luckily when we focus more on interior elements, it's not as frequently washed as wearables, right? I guess people working more on wearables get more of that. But yeah, privacy, so most if not all of our projects, we kind of avoid by all means gathering personal data and like clouding it, unlike other kind of, I guess, commercialized products that focus more on collecting as much data as possible from people and then uploading it to cloud servers. We kind of focus more on giving the real-time experience with the user rather than just collecting data about them for further personalization. But yeah, what else?
Can I'm just going to decode a little bit of this. They weren't necessarily asking about the collection of data, but actually where the garment or the entity, the hat or whatever, can change color to say, oh yeah, there's that person. The person wearing those electronics, we need to talk to that person or something like that.
Okay, that reminds me actually some of the data we collected in a user study that we did with the table runner, the interactive tablecloth. In that study, people were having dinner together as 6 friends around that, and they were actually saying, oh, it's changing more on your side because you're not talking enough with us. Or, oh, it's interacting more to you when you talk more. And it was really interesting because it wasn't doing that, but people gave it meanings beyond what it was designed for. And it was quite interesting. And people did weird things with it, even though it was absolutely not anthropomorphic or zoomorphic in any way. They kind of like petted it when it bumped up, and they were kind of like patting it down to cool down. And some people were warming it as if there was some sort of aura around it. So definitely people engaged with these things in unexpected ways, let's put it that way.
Okay, there's some more questions from our virtual audience, but it is almost 5:15, and we do have another event happening a little bit later, and there's the poster sessions right now. So if it's all right, you will close this session, and thank you very much for your wonderful presentation.
Thank you so much. Thank you.
Don't forget the office number. Her office number is up on the slide. You'll be able to go visit. Where else?